Hello, everyone. Good morning, good afternoon, good evening, depends on where you are, and welcome to the Generative and Agentic AGI workshop. I'm really delighted to host and chair this session, which is possible thanks to AGI Foundation. So thanks a lot to the foundation to have found and created the space for this event to happen. And obviously, it's possible because three key people from Intel, ForestHub, and Mito Tech accepted with me to create contents for you to share. So today we are going to have a pretty intensive period, I would say 3 hours and a half. And but before to enter into the different sessions, I would like to quickly remind that this type of events, this workshop, the forum, are possible because our initiatives organized by the Generative AGI working group that I have the privilege to share. And the mission of the working group is to make sure different entities from academia, industry, and even the individuals can share this space to cooperate, propose innovation, to substantiate the happening of generative AI at the edge in different ways, through sharing materials as today, through education, through networking, and presenting any achievements that has the merit to be shared. So please, in the next period, consider to contact me if you have great stuff to share, such that we have this container which in time, which help any of you to share really that. And I would like to remind that I am the chair as the working group founder. And I would like also to remind that Professor Ajar Musanif, she was the co-founder with me, and he was a past co-chair. And today, in this period, we have as, since time also, we have as a current co-chair, Professor Roberto Morabito from Technical University of Denmark. So I wanted to remind these people, please have a look to our wiki, which is very populated of articles and stuff. So have a snapshot of this QR code in the wiki, which is organized by the AGI Foundation. There are several working groups. One of these is Generative AGI. There is great content. Please feel free to review it and maybe also to suggest improvements because this is public. Then I would like also to set the stage. So we are here because generative AGI is super important. And how does it relate to tiny machine learning? Well, you know, since 2018, when TinyML Foundation was set, through the years, it was the principal technology we all worked about. But through the time, you know, the technology evolves, gets more complicated, and offer more functionalities, and generate more opportunities, and also is characterized by breakthrough features. So today the situation changed, and be reassured that this is not only my opinion. I think is quite an objective type of statement. So TinyML today is a kind of edge filter. Yeah, you can run classifications, detections, and all these type of workloads, but then these are filter instrumental to the generative AGI, which is essentially act as an intelligent middleware to translate such edge filtered data into contextualized actions to make sure that the machine are autonomous. Today, you will see that statement substantiated in practice. And I don't want to spoil anything, but really stay with us until the end, because you will have demonstration that these are not just words. And then, as I say, that's not my opinion. I mean, since 2024, we ran 5 forums, each one 2 days, each one with between 8 and 12 speakers from different industries, from different universities. And the distilled situation is that hardware is there. More than 18 chip vendors offer solutions, hardware solutions, things which you can touch in hardware for edge language model. And this is counting, it's not at the end. But then hardware need software and need ecosystem. The ecosystem is established. There are frameworks, there are foundational models, there are procedures to customize the models, there are software toolchain and suites for the deployment. Today, you will see this happening once again. All the verticals are concerned. Tell me which one is not touched by generative edge AI, and I will amend my list. That's to achieve scalability. We all know that at the edge is super important to achieve scalability. Generative AI on the supercomputers cannot scale. Just imagine how many Android and iOS users you have around the globe. I mean, there is no supercomputer that can offer simultaneous generative system AI services to all of them, be attached to these supercomputers. Physical AI is a perfect example of deployment of language model to the edge, robotics, just to make an example. But I would say more in general, from sensing to reasoning to elaborate and generate actions. So that's a robot, sure, but this can be also drones, can be skeletons, can be any type of system, can be consumer devices that you can think of. Multimodality, because sensor is not just images. We should not speak anymore about visual language models, but heterogeneous sensing language models. And agents. Agents, today we are focused on agents, and you will see brilliant examples of how from Intel, ForestHub, and from Mito technologies, you will see how these can be implemented at the edge with in a number of use cases and with a number of performances. And then this is the agenda, essentially. So number 1, we will have the first workshop. The contributors are Intel and myself from STMicroelectronics, and Lorenzo Mazzone, which is supervised, the internship supervised by me. And will last for 1 hour and a half, so please sit comfortably. From Intel, we will have Ashutosh Kumar, Ph.D, M.B.A, which is lead of technical marketing at Intel, which also provided us an astonishing developer cloud to let you play with it. That's brilliant. Thanks, Ashutosh. Number 2, for an hour, we will have Marcus Rueb, from which is the CEO of ForestHub, which will show in practice how to deploy tiny agents, which are cooperative, with a proper protocol all over the home. That's fantastic. It will use also ST components. And then, such as the STM32MP2, the STM32N6. And then we will have, last but not least, Andrea Basso from Mito Tech Ventures, which will present the narrative camera. I mean, the narrative camera is a brilliant example of, along with the Intel one and the ForestHub one, of what I was saying. TinyML edge filtering, and then the middleware is generative AI. And you know that this is important to digest to all of us, because this will have enormous implications on the hardware, on the software, on the application, and so on and so forth. So I will stop here. I hope you will enjoy this time. And now I think it's time to enter in the first session in the workshop one with Ashutosh Kumar and Lorenzo Mazzone and myself. Essentially, the sequence will be: first, I will present an overview of what has been done, and which a kind of introduction, technical introduction of the workshop number one. Then Ashutosh Kumar will introduce OpenVINO and the Intel Edge systems, which will be used during the workshop one. And then Lorenzo Mazzone will guide you through the practical deployment of a conversational speech audio into the Intel systems, which Intel made available kindly to all of you, to some of you, because these are not infinite resources, through the Intel Developer Cloud. So without further ado, if you have comments, don't hesitate to share in the chat window, and hope you will enjoy this. That for us is a great time to share a number of technology that I hope you will enjoy. Hi, Ashutosh. It's a privilege to be with you today, and thanks for your hard work to make sure Intel is the main actor today during the workshop one, which is very important for the workshop, for the working group, but I think is more even important for the community.
Yeah, thank you for having me, Danilo, and looking forward to an amazing, engaging session.
Excellent. Thank you, Ashutosh. Rosina, if you allow me, I will start with the second presentation, so to introduce the workshop one and the conversational audio. Thank you. Very good. Thanks a lot, Rosina. So I'm going to run these few slides. I will give you an overview, main concepts, just to make easier the understanding to all of you. So workshop one is about conversational agents. Why these are important? Because we need to make sure that the human-machine interaction is really made available in a comfortable way to the users. And so it's natural, it's speech driven, and so on. And this has to be deployed. And to deploy, we need proper hardware. For example, the Intel Edge AI solution, complemented by the Intel OpenVINO software framework. So conversation essentially is an essential need for all of us, and is a touch at distance. There have been studies where children were interacting with parents following a stressful event. And there are different ways to interact with the parents. We are used to use instant messaging. We'll all use that, but that is not a very convenient way to interact following stressful events. There are studies that I mentioned in this slide. The obvious proper way to handle that is by full physical contact. Let's meet together in person. Let's touch. Let's make sure that the children are comforted after these events. That would be ideal. Sometimes it's not possible. So, parents are busy, are working, and the life of everyone is maybe busy, and so speaking with these people, with the children, is something that we all experience as parents. And this has been measured to be quantitatively equivalent to the physical contact. And that's very important because it lowers the cortisol, it lowers the stress level, similarly approximating the shape of the cortisol decrease achieved through the physical contact. And there are already practical examples of that. For example, NVIDIA produced Personaplex through 7 billion language model, which really give a very enjoyable interaction with the machine. You will laugh using this, hearing this demonstration. So it really has an effect on all of us, and it covers a basic needs. Technology is very effective when it covers human basic needs. And also it's a biological medicine, because through speeches we can interact as human, we can clear misunderstandings and avoid fighting. And also vocalization allows a release of oxytocin, which is the hormone of trust and bonding. And this is important because it's the basis of a positive relationship between humans. And third, through interactive conversation, we stimulate the Broca area of the brain, which also control it's an intermediator between our thoughts and the way we'll actuate them through our tongue and our voice. So it's very important. So you see that conversations are very important for us. Then we need to deploy conversation. But here, to understand that, we need to be aware that what is the edge, what is the mother edge. So we started with TinyML. TinyML were and are today microcontrollers and sensors, which are essentially edge helpers. But then the middleware and the intelligent middleware is the generative edge AI, which expand until the supercomputer. And so this red line is the boundary. So you see that the boundary moved from the microcontroller to the on-premises devices. And today, edge means also consumer devices enabling conversational interface, which we will talk about today, and will cover also near user computing. And one focus of the workshop one is to substantiate how to use the near user computer, for example, the Intel solutions. And then we have the on-premises server. So you have to understand that the edge in just, I would say, maybe 2-3 years, radically changed from what it was TinyML. Obviously, the boundary is sharp. We are not on the supercomputer. That's for other things. And the power consumption is order of magnitude. The gap in terms of power consumption is order of magnitude between the supercomputer and all these processors that are composing the modern edge. Furthermore, we focused on this workshop on the Intel near user computer. For example, I had a brilliant suggestion from Ashutosh to use the CADAS, featuring the Intel Lunar Lake, which is a very powerful SoC with a unified memory architecture, very powerful, with a lot of resources, CPU, GPU, neural processing unit, to achieve more than 100 terop, and to avoid any dependency on the cloud, and also having a platform where to develop solutions which are low latency and very low in terms of power consumption. And then to achieve what? Well, essentially, me and Lorenzo, we wanted to investigate how to build a modular framework, we were not in love with any particular generative AI workload. We wanted to be as agnostic, as generic as possible, given the computing resources of the Lunar Lake in the CADAs. I know that Ashutosh will cover also other Intel processors. And to create a software architecture to plug and play speech-to-text, language model, and text-to-speech, including end-to-end models. You will see. So these were more than 30 models which deployed on the different assets of the Intel processor were counting about 700 plus different pipelines, considering even more, 3,300 possible deployments, considering the different assets that we have in the Intel SoC. So CPU, NPU, and GPU hardware. And we developed a framework which is rich. So, for example, I'm not going to name all the algorithms, but I remember clearly, for example, Moonshine, Whisper, in terms of LLM, Quen, small m, Gemma, in terms of TTS, text-to-speech, Piper, Kokoro, and others. And also in terms of end-to-end pipeline, you know, with these 3 blocks, you can build the conversational agent. But imagine that you don't want to build through these blocks, and then there are the liquid AI solutions that allows you to create a full pipeline. So really, we were using a lot of models, and also these were characterized in terms of word error rate, which essentially measure quantitatively the percentage of words which are incorrectly transcribed by the speech-to-text, and then the real-time factor. The real-time factor says essentially how the machine is fast in processing the audio at the input. We would like to have an RTF as lower as possible than 1. And then in terms of word error rate, ideally, we would like to be close to 0. So performances that Lorenzo measured in terms of, for speech-to-text, Whisper Tiny was the lowest in terms of real-time factor, while Full SR Nano was the lowest in terms of word error rate. These on the Intel GPU. Then in terms of speech-to-text, Moonshine was the lowest in terms of real-time factor, and QN3 in terms of word error rate. And this was on Intel CPU. And then the TTS was Piper. And so Piper was having the very minimal RTF, and Kokoro the minimal MOS. What is MOS? Minimum opinion score. So essentially, Lorenzo conducted among 85 engineers in a full anonymized way an evaluation for, this was a subjective type of team, to evaluate the voice quality on a scale between 1 and 5. So you know that it's difficult to build a team of for subjective assessment. So Lorenzo did it, and a lot of people accepted to contribute. And I think this is very valuable. And TTS were both on the Intel GPU and Intel CPU. So the key performance metric on the language model, essentially, the Q1 2.5, 1.5 parameter was accelerated by the Intel NPU at 20 tokens per second with a semantic accuracy of 85%, and with very good results also in terms of benchmarking on the Stanford question answering dataset to test the factual question answering capabilities. So the winning pipeline over all these complex framework was, in terms of speech-to-text, moonshine, tiny, 0.03536 for RTF on CPU, 0.069 in terms of word error rate, QN 2.5 with the performances I just comment, and Piper, and that was, let's say, the one that we selected for a demonstration. Obviously, also the other models are available, and you can access the GitHub Lorenzo Mazzone set, so you can you can enjoy this, and please report any feedback on this GitHub. We would love to hear from you. There is a publication we just submitted to MTPI Applied Sciences. It was an invited paper, and this is under scrutiny. So it will take a while to go through the reviewers and all of that. And hopefully it will be available as openly available paper. So I stop here. I leave the floor to Ashutosh and then to Lorenzo. Thank you very much. So please, Ashutosh, come on video, and I leave the floor to you.
Bring me in. Okay, awesome. So I am going to start sharing my screen, and hopefully everyone can see my screen. So welcome everyone, and thank you, Danilo, for amazing introduction of the workshop. So I am going to briefly give you an introduction of what OpenVINO enables you to do on Intel processors. Before we dive into that, as Danilo mentioned, you will get access to these Intel Core Ultra processor instances to try the workshop during this session, as Lorenzo walks you through on different steps to run this entire pipeline that Danilo was just showing. So let's get ready to get you access to those instances. Standard notices and disclaimers. So let me first walk you through getting your access. So go to this link. Please start signing up because it will be important that you can try hands-on with different processes, as Danilo was showing, CPU, GPU, and NPU in Intel Core Ultra SoC. You can try different compute capabilities and run these pipelines yourselves. So please go to cloud.intel.com/AIPC. Okay, and on the top right, you will see this sign in, sign up button. Click on that link. So I'm going to walk you through a little bit as well. So here, click on that link, and it will take you to this page. If you do not have an account already created with Intel, you can just add your email. Make sure, so one thing I want to ensure that make sure you use either a company account or a university account. Your personal accounts like Gmail or Yahoo or other mails will not be approved because those get filtered out. So make sure you use your company account or your university account. Just go add that. So for example, if I add a specific email and then go next, and then finish your account creation. As Danilo had also mentioned that we don't have infinite resources to add everyone. So first 25 users will get access to the instance that is powered by Intel Core Ultra Series 2 processors, including Lunar Lake. And we have another series of processor codenamed Arrow Lake that is also Intel Core Ultra Series 2. So you will get one of those instances to try it out. So please finish this account first before we can proceed to signing in, because before you can proceed to get an access. So I'm going to give you a minute to finish this account sign in. once you have signed into this account, like created your account with, make sure you are using either a university account or a company account. Once you have receive your you have your account, go back to this cloud.intel.com/AIPC and log in with that account. And then go into the section to where it shows you hardware catalog. So I'm going to walk you through a little bit in here. Okay, so you go into this hardware catalog. Once you have logged in, once you registered your university ID and then a university or company ID with intel.com, and then you log into cloud.intel.com/AIPC, you will get to this page. Then you click on hardware catalog and you see this top section. This is what you are going to request. Sorry, not the top section. Lunar Lake is here. This is the section you are going to request for Intel Core Ultra Series 2. So you go in here, you add an instance name. Let's say, I don't know, workshop test Ashutosh. Now this is important, intended use. So I'm going back to my slide. Once you click on this link to actually request access for Lunar Lake processor, intended use, please include Edge AI 2026 as in here, right? So Edge AI 2026. Okay, please enter that. Once again, in the intended use, please enter Edge AI 2026. Then you can go into additional detail. Actually, here, not additional detail, you don't need that. Here, if it asks for it, right now it doesn't show, you can request AIPC workshop event. So you can just request AIPC or general use. So I'm going to put this. Okay. And make sure you have this Edge AI 2026 in the intended use, and then you can go and request instance. Okay. So I'm hoping you will you have requested that instance. So after that, it will take a minute or so to get approval while I give you an introduction on OpenVINO, and then Lorenzo will help you walk through this entire workshop on the instance that you get access to. So again, just quick repetition. Once you log into cloud.intel.com/AIPC using your university or company account, you can go to the hardware catalog, click in there, and then click access for the Lunar Lake AIPC and add an instance name. Make sure you have added intended use as Edge AI 2026. and then request instance. Okay, while you finish those, I am going to quickly give you a brief introduction of what OpenVINO does and how you're able to run all these like generative AI models on the Core Ultra SoC. And remember, the Core Ultra SoC that Danilo was showing about the Cadence Mind units, these are also in some of your laptops, PCs, which are powered by the Intel Core Ultra processor. So you can do these things. You can take advantage of OpenVINO to run these workloads on your day-to-day developer laptops. So what is OpenVINO? So most of the developers develop in many different frameworks from PyTorch, TensorFlow, Onyx, Keras, Paddle. OpenVINO gives you a unified API to take advantage of many different processor and compute capabilities that Intel has. So you can easily convert models from your choice of frameworks and then get it optimized to run on Intel hardware. It can be as low as Intel Atom processors, which are kind of like Raspberry Pi type of compute capabilities, like tiny edge devices. And then you have like Intel Core processors, Xeon for server class CPUs, and the Intel Core Ultra, which has a heterogeneous accelerator architecture with CPU, GPU, NPU. You can also run OpenVINO on ARM CPUs. And then different GPU architectures that are available on Intel devices, as well as the NPU devices that Danilo was also showcasing. You can take OpenVINO models and deploy it on Windows OS, Linux OS, and Mac OS. For today's workshop, we will be utilizing Windows OS. The philosophy of OpenVINO is basically enabling you to write your code once, and then it is scalably deployable across your edge devices, your AI PCs, your cloud infrastructure with Xeon processors, and even robotics use cases where you have Intel processors to run your AI workloads. It helps you reduce the memory footprint of the model. So there are compression frameworks, and it's completely open source. There is neural network compression framework that we utilize to compress your model to int4, int8 to provide you faster inference speed and reduce the memory footprint with smaller model size, smaller binary size, lower number of activated weights, etc. And we also provide you with specific generative AI APIs within OpenVINO Gen AI that helps you with accelerating and simplifying the generative AI deployments on Intel. These are super simple Python or C++ APIs that, depending on what kind of applications you are building, you just need like 4 or 5 lines of code to basically use that API, and you can run it across edge devices, across devices from client to edge to cloud. And similarly for physical AI, we also optimize some of these state-of-the-art vision language action models. You can use open source tools like LeRobot or other capabilities or Physical AI Studio that we have created. You can take those workflows to build your fine-tuned VLA models, and then use OpenVINO Physical AI framework to basically optimize it for maximum throughput and improved latency on Intel devices. There is a large ecosystem that OpenVINO integrates with, where you might already be developing Hugging Face. There is a huge set of models available on Hugging Face, or you can also use Optimum Intel capabilities on Hugging Face to actually convert models, generative AI models to OpenVINO. You can use Onyx Runtime, you can use Llama CPP, or even LiteRT, which used to be TensorFlow Lite, TF Lite before, Olama, PyTorch, Windows ML, Models Beat, any type of type of frameworks that you are using for your deployment workflows. OpenVINO integration is available. Or if you're trying to build large-scale model serving capabilities using VLLM or Spark or even Triton inference server, for data center type of workloads, you can utilize OpenVINO there as well. And for different types of graphical interface based UIs to actually utilize an OpenVINO for optimized performance. You can use things like Llama Index, Audacity, etc. So there is a large ecosystem where OpenVINO supports you to take advantage of fast inference on Intel processors. So now we are getting close to giving Lorenzo the ball to basically walk you through different steps and have you experience the workshop yourself. So you can learn more about OpenVINO on openvino.ai or docs.openvino.ai. You can go to GitHub to see try out different notebooks and demos that are already available. There are hundreds of notebooks that help you try different workflows for even model optimization, model conversion, etc. And this Lorenzo is going to walk you through these steps, but at this point, I'm hoping that some of you have been able to get access. If you have not, please write to me, and we can get you, like if it's pending approval, we can get you approved quickly so that you can walk through and experience the workshop yourself. So again, just to close, I'm going to just give you an in case people joining late, just walk you through quickly. Go to cloud.intel.com/AIPC, sign in, and make sure you use your university and company account, and then go to hardware catalog, request your Luna Lake processor, and make sure you enter your instance name, intended use as AJI 2026, and request instance. And then we can get started. So Lorenzo, you are ready to take the workshop?
Yeah.
All right. Off to you.
So hi everyone. Thanks a lot, Ashutosh, and thanks a lot, Danilo, for the interesting introduction. And so I'm gonna now, and thank you all, of course, for being here and watching this workshop. Let me just create. Okay, I will share my screen now. Okay. Let me know if you're able to see. Should be okay. So now we'll work through all the steps needed to let the demo work fine. And of course, if you have any questions, feel free to interrupt me, write on the chat. Actually, I'm not sure that from here I'm able to see your messages, but maybe I will check during the steps if there are any questions or any trouble. So let's begin. If you have access on your DevCloud PC, you will just have to go on here on your terminal and open your terminal. Here you can click yes. So, okay, I hope that everything is clear and visible. So first of all, we will have to clone our repository, our GitHub repository with the git clone command. So we'll have to git clone https /s. I will apologize right now for any type of typing mistakes that might happen. github.com/Mazzone Lorenzo 1/conversational edge model.git. Okay. For every step, I will just copy and paste for you on the chat, so that's easier for you to just copy and paste all the commands. You will find in the general chat all the commands. So first step is done. Now we'll have to change our directory into the repository that we just cloned. So conversational edge model. Perfect. I will go slow so that everyone is able to follow easily. Then we will have to create our Python environment. So Python -m venv space.temp. Okay. It will take a little time, but not so much, hopefully. In the meantime, I will copy and paste the command in the chat for you. Okay. Now we have to activate our environment. Then the scripts and activate. Okay, perfect. And for the Python version requirements, 3.10, 3.12 is recommended. Yes. Okay. Now that our environment is activated, first of all, we need to upgrade our pip module. So Python -m pip install --upgrade pip. Okay. Okay. Now this is installed. We have to install the requirements needed to let our demo work. So Python -m pip install -r notebook requirements .txt. Okay. It will take a little time. Let me, in the meantime, copy and paste the command for you to paste it on your cloud device. So while these requirements are being downloaded, this notebook was specifically made for this workshop here. So it's a Colab notebook. It was the easiest way to let you try with your hands on the dev PC. But on the repository, not the one that, on the repository that we're using now, the conversational edge model, You can also find actually the actual demo that you can download and let run on your Intel PC. It has a pretty graphic user interface, at least a little better than the Colab notebook, and it's a little bit more responsive, a little bit more fast. Of course, here all the streaming that is made through the LLM module, between the LLM module and the text-to-speech module is not possible, of course, on the notebook. On the demo that we implemented, these optimization are present, so it's a little bit more fast and a little bit more easy to use for you. And you can find all the instructions to download it and run it on the repository. This repository here, conversational edge model. Here you will also find the link to the other repository, the one that Danilo shared before, with all the code that we implemented to test all the various models, all the statistics, also the energy consumptions of all the models, so that you have a wider idea of why we choose those models, those three models, Moonshine, Quen, and Piper. And also you can see all the tests that we've made, and you can test yourself, of course. All the instructions are there too for you to try. So yeah, also if you have any question, feel free to reach me and feel free to ask also in the chat. Let me check if there are questions. I don't see any question apparently, aside from the Python version requirements, which I answered before. Okay. For those who are connecting now and maybe didn't have the access on the Dev Cloud, you can find all the commands here in the chat. And if you type them and paste them in order, you will have no problem and no issue in trying them yourself, even if you weren't able to join us before. Okay, now that everything is set, we are ready to open our Jupyter notebook. So we just type, we need before actually to activate our kernel. So Python -m API kernel install --user, then -name equals workshop venv. Oh, typing mistake. No, actually it's fine. -venv display name equals commas Python bracket workshop.venv. A little space here. Okay, I hope I didn't miss anything. Okay, should be fine. Now we have to open our Jupyter Lab. Oh, let me type and paste for you in the chat the command. Okay. Okay, now we can open our Jupyter Lab. It will take a little time. Don't worry if when you type this command, this is perfectly fine. You will just have to close this tab and then control click on this first link here, where you see or copy and paste one of these URLs, and just control click on the first one, and the Jupyter Lab will open. Now, here you can see all the information needed. You can also find all the commands that we just typed. You will find information for Windows PowerShell and both also macOS interfaces and systems. So we can actually, let me see if there are some questions. I will check sometime the chat to see if everything is fine and everything is working. So we can start running our notebook. You just have to press on the first cell and run this cell and advance. We will now check if everything is correct with the requirements. So dependencies installed, everything is fine, we can go on. Okay, for the second cell, we check if the routes and the path are set and are correct. Let's see if everything is fine, hopefully. Okay, this seems good. Now, for the next cell, it will load a little preview of an audio. It's just an annoying audio with a lot of information and general speech on Edge AI. We choose a sample like this because it was a long text with some technical language. And let's say it was a good stress test for a presentation demo to see the actual performances and the actual capacities of these models. We will load now all the 3 modules. This is the code is made modularly, so you can, if you want to add modules, you can. If you want to change the models, now we'll load the ones that we implemented. Okay, perfect. Okay, now I will load the final display model loader. Here you can choose on which device you want to test the small language model, the QAN model. For Piper and Moonshine, those 2 models are already really small in the terms of 20 million parameters, even less. And so there was no need, they're really efficient, there was no need to optimize them on OpenVINO. But for the QAN module, actually, we had a lot of benefit in running that model on both GPU and NPU. So I suggest you to choose GPU is the one that in this configuration gave us the best results, but you can try and test on whatever module you prefer. So it will take a little time, but not so much, hopefully. And yeah, after this is finished, we can run our final demo. And you can also try and test with your own MP4 files. I'm sorry, WAV files, audio files. You just have to access on your dev cloud to your Drive, Google Drive, or whatever you prefer, and then upload here your audio. Here you can see the list of audio files that are ready to be as an input for the demo. We have now just the sample that we prepared. But if you click on upload and you have downloaded your own, in the meantime, I start running pipeline, your own audio, you can then just click refresh list and the audio will magically appear here. So now you will see that that's it. That's the transcript of the input text that we gave to the model.
As an AI language model, I am designed to provide information and assistance based on factual knowledge and ethical considerations. However, my responses may not reflect current events or trends in technology. In this case, While there has been significant progress in AI and computer architecture, it's important to note.
For the sake of brevity, I will just stop it right there. And but as you can see, it's really quick, almost real time. Also bear in mind, this is working on a dev cloud, not on your local PC, and there are no optimization made. So of course, this can be even more optimized. As I was saying before, we made it on our demo that you can find and try yourself on the GitHub repository. Here it's the chat. You can see the input text, and that's the answer of the model. It's just what the model thinks about the Edge AI in general, its advantages, and yeah, just an opinion. And here you can find also some interesting metrics. As you can see here, approximately 72 tokens per second, really a lot. Also Piper was really fast. Here you can also find the RTF of the Moonshine model, just 0.04. And yeah, that's pretty much it for the demo. Here you can also find all the models in the workshop directory. Everything is made thanks also to Ashutosh modularly, and you can find every aspect of the code. You can investigate and try yourself and make any changes that you prefer. So yeah, I'm checking if there are some other questions. I don't see any questions, if I'm correctly. As I was saying, if you have any more questions, any more curiosities, just feel free to reach me and to write me. You can find my contacts on the on my GitHub repository. And yeah, thanks again for listening. I hope you enjoyed our little demo, our little presentation. And yeah, that's it. That's it for me. I will now leave the word to Danilo and Ashutosh, and can work through the workflow. Yeah, sure. Here, as I was saying, if that's what we mean, you can see all the code, all the different modules implemented. As I was saying, everything is modular. So this was made in order to have our code more, let's say, fixed as possible, more changeable, of course, as possible, so that if anyone wants to upgrade or just for the sake of curiosity try on other models, it can just change one module, load it, and make it work, of course, with the others, and then create his own pipeline. So of every module, the text-to-speech model, of course, has a synthesize to file module, and yeah, of course, there are the OpenVINO wrappers in order to have the Quen model optimized, and in order to also make you able to select between which specific hardware you prefer to run the models. I'm sorry. So if you want to run it on CPU, if you want to run it on NPU, or if you want to run it on GPU, that is up to you, and you can make all the experiments that you prefer. And here you can find also the code for the metrics that appeared at the end here of pipeline for every model. Here also the load models so that you can see all the models being uploaded. That's the code for the large language model, the QAN module. As you can see here, optimized for OpenVINO, in which you can choose the preferred hardware. And also, the model comes with an extraction prompt so that the agent can remember some personal facts, some specific facts about the user, and it's personalized to try and help you as much as possible, based also on your preferences and on your past messages. So to make it as more useful as possible, let's say. Yeah, and I think that's it. I don't know, Ashutosh, if oh, there's actually an error here. So let me just read real quick the questions in the notebook. When I click load model, it said loading load fail. Not send a request as client has been closed. That's pretty strange. Yeah, but I see here that Ashutosh actually already answered you. So I hope that this issue has been resolved. Actually, it's being resolved right now. Yeah, maybe trying again from the beginning, it's the best option, probably. So yeah, now I think is also that's fine for Ashutosh and Danilo. That should be it for my part. Again, if you have any other questions, any other curiosity about our work, about my work, feel free to reach me and reach Danilo and reach Ashutosh. I think I can talk for everyone here. So thank you again. Thank you again for being here. And yeah, I will leave now the word to Danilo and Ashutosh.
Thank you, Lorenzo. Very well done. And thanks also to Ashutosh to enable all of that. Maybe, Lorenzo, you worked a lot with OpenVINO and with the CADAS and Intel solutions, allowing all these amazing amount of combinations,
Yes.
Spreading the workloads on the different assets in the Intel SoC. So put yourself in the shoes of a developer, okay? You did it, essentially. You just proven. Can you share some, let's say, comments about your experience, your journey on OpenVINO, on the Intel, from a user point of view?
Yeah.
Yeah.
Well, actually, it was really interesting and I really enjoyed trying with new models being optimized with OpenVINO. And for what I saw and for what was my research, I saw that huge optimizations were possible with OpenVINO. There are a lot of also let's say tutorials on GitHub on how to implement and how to build your wrapper, OpenVINO wrapper for a lot of specific models. Actually, our research was on the audio models in general. So text-to-speech and speech-to-text, which, let's say, with respect to these large language models and small language models, are a little more, let's say, niche, if we can say. And even that being said, a lot of audio models were optimized and ready to be deployed on and run on OpenVINO. Also, during my research, I saw that with the OpenVINO optimization and being able to run those models on the specific neural unit or GPU, we saw actually an improvement in terms of efficiency and let's say energy consumption in general. Because of course, these models were optimized, had a better inference, really better inference, and let's say the system came back to the idle system in a way that was, of course, faster. So that, of course, gave us a lot of benefits in terms of, as I was saying, efficiency and energy consumption in general. And beside that, of course, as I was saying, the inference for the majority of the models that I tried with OpenVINO really had a huge benefit. And yeah, of course, as I know, a lot of models are being optimized right now and will be published in the future. Maybe the work that I've done for now, it's already old because maybe there are already new models that have been deployed that I didn't have the pleasure to deploy and test. But yeah, from my point of view, it was really interesting. I saw a lot of
Lorenzo, thanks. Another question is the following. You know, you are going to be graduated soon on computer science master at the University Milano Bicocca.
Yes.
So essentially, you are the prototype in our little statistics, obviously, of a very, very young professional. I mean,
yeah,
just a computer science guy that approach generative edge AI and approach Intel SoC and approach the framework, the OpenVINO framework. So what I'm saying is that what I need to know from you, I think is interesting for all the community, how easy was for you to be up to speed?
Well,
I mean, you started from scratch, right?
Yeah.
I mean, at the beginning of your internship with me, you started from scratch. And then you grew competence, knowledge on the platform of OpenVINO and so on. So how easy, how much time did you, let's say, what was your experience in terms of productive learning from scratch to be up to speed, you know, on mixing and matching, not just mixing and matching the models, that's a separate thing, but just to be enough competent to start. How fast was this process?
Well, not so immediate, of course, because of course the competence that you learn in university are just a part of the knowledge that you need to have to fully understand and fully be able to deploy everything on edge. Of course, it's even bigger challenge to deploy models on the edge because of obvious reasons. You know, they are still powerful devices, but of course energy constrained for obvious reason. So it wasn't immediate, but I needed a little bit of time, a little bit of study.
It was not immediate because clearly you started from scratch without existing pre-knowledge. Without existing, that's clear. It would be the same for everyone.
But I found the documentation, the OpenVINO documentation, and also all the online documentation that I also found really useful and really helpful in helping me try and learn and develop and being able to acquire all the needed knowledge to try and, let's say, master all those techniques and all those skills required to develop such models. So it wasn't immediate, but also it wasn't that too hard. Of course, I had my computer science background, so it was from scratch, but not from zero, let's say. So but it was really interesting, and I really enjoyed it so much. As I was saying, the documentation was really helpful, trying to study and understand all the different architecture of the different models, and also of the different hardware that Intel provided to me and to us. So
one thing I remember, correct me if I'm wrong, Lorenzo, is that you did not require, and also Ashutosh can witness that, you didn't require support. I mean, usually support is provided by the field applications and engineers, but I think you didn't need that, right? This is a sign of how relatively easy was all the journey, because
of course,
because the more you find roadblocks, the more you need support, the more it means that from one reason or the other, the journey is not simple. But in your case, it was not the case, right?
No, exactly. If you're already a skilled person in the let's say in the topic, but in generally speaking, in AI topic and computer science topic, it's as we were saying, starting from scratch and being able to develop everything is not immediate, of course, but it's not hard either. You will just have to study a little. Of course, a little study is required, as everything in life, but it's not something so hard. And
so Lorenzo, in other words, I would say that a professional, you are a professional, but you are young, right?
I'm trying.
Obviously, I was young as well many years ago, but that's the case. So a professional should have an easy life with
definitely.
Yeah, that's the conclusion.
I totally agree.
Okay, very good. Ashutosh, to you, any further comments or any concluding remark, please?
Definitely. And thank you, Lorenzo, for sharing your experience with OpenVINO. What we are trying to do at Intel with not just OpenVINO, we also have a project, open source project called Open Edge Platform that I have presented before in this forum, Edge AI Foundation forum. We are trying to basically help make developers' life easier. When we start building Edge AI projects, first thing, like typically our thought goes that, oh, do I need a GPU to run, a discrete GPU to run all these generative AI models? There are so many optimized models that can be run on the devices that you are using in daily lives, right? Like an AI PC, for example, or a small Nook form factor, or the Cadus Mind PC that Lorenzo and Danilo are using, powered by. I'm just giving an Intel example. There are, of course, other community hardware community examples available, right? Where we can run these powerful Edge AI workflows. And the advantage of this, like heterogeneity with CPU being able to run a small CNN or even speech to text or text to speech. In this particular example, being able to use GPU to run a larger LLM model. And then there is NPU as well available to run another model. We can actually build a lot of useful applications that takes advantage of all these compute resources that we have available and build that entire pipeline running on a small, compact edge device.
Very good. And Ashutosh, to conclude, call for action. What do you recommend the community to do tomorrow morning after this wonderful workshop?
Yeah, definitely. I have shared some resources on OpenVINO in the chat as well. Feel free to try it out. If you have an Intel laptop that you are using for your regular development, you would be surprised what you can run using OpenVINO on that laptop. You don't need to go buy a separate machine or even a small Atom device that Atom-based single compute board, those kind of things that you can buy off the shelf reasonably cheap, and then you can try these out. Then there is the Open Edge platform capabilities. Like if you're already building applications for specific verticals, Danilo mentioned so many different verticals that are touched and empowered by Edge AI, be it smart cities use cases that you are building a traffic management type of scenarios, monitoring all the traffic intersection cameras, weather sensors, all those things, or a robotics use case. There are a lot of resources available on OpenEdge platform, docs.openedgeplatform.intel.com, as well as OpenEdge platform GitHub and OpenVINO GitHub. That can enable you to understand how can you build an optimized video analytics pipeline or an optimized video live captioning pipeline. So using generative AI models. The processor, the system that we used in today's workshop is Intel Core Ultra Series 2 from last year's. That was launched last year in 2025. This year, the processor we launched, it was called Panther Lake, and it has close to 200 TOPS of AI compute capability, and you can run even more powerful. Like just recently, last couple of weeks ago, I think we released optimization work of running a 35 billion parameter Qwen 3.6 model on Core Ultra Series 3 processor. We wouldn't imagine that like we can run such a powerful model in the same laptop that I'm using.
Very good. It has been really a pleasure and a privilege to be with you today, Ashutosh and Lorenzo. And congratulations for your contribution to the success of this workshop. And in particular, Lorenzo, you did a really wonderful job here.
Thanks.
And I hope your GitHub will be used by many people. And so feel free to report the success of this repo.
Sure, I will now maybe copy and paste the link here in the chat.
Yeah. And Ashutosh, I think it was very important to have Intel, you and Intel in this workshop. I think this will reinforce the cooperative attitude we have in the working group and in the larger foundation. And I think this was really an important example. Thank you so much.
Thank you for having me.
Thank you so much.
Yeah.
Thank you.
Thanks a lot again. It's been a pleasure for me. And I hope you enjoyed the presentation.
Very good. And now I think it's time to switch to the second workshop. Ciao, Ashutosh. And the second workshop is with Marcus. Ciao, Marcus. Now,
Hi,
ciao, Marcus. Before I leave you the floor, obviously, let me say a couple of words. So to the people which are connected. So, you know, the brilliant things start when good people relate, at least in my opinion, relate and enjoy cooperating. I'm not making philosophy here. But I want to underline that this is the result. What Marcus is going to show is the results of networking we did during the AGI Foundation event in San Diego. I think it was a brilliant example of networking. And to make it really concrete, with Marcus, we shared enthusiasm, an idea, and then this idea, Marcus make it for real, and is the subject of the workshop, which is the self-driving home, tiny agents cooperating over tiny A2A on STM32. So thanks, Marcus, also to use ST components, and the floor is yours.
Thank you very much, Danilo. Thank you. Yeah, and like Danilo said, this workshop is the result of a really good talk with Danilo in San Diego. We just standing there, had thinking about agents use cases, and then he told me about his smart home experience and so on, and then we talked about smart home, and then we had an idea how agents can make smart home even better and even more cooler. And this was the inspiration for this. And then Danilo said really fast, "Hey, I sent you some boards over, and let's make a case out of this." And yeah, so I'm now share my screen, and yes, now you should see it. So yeah, first, some words about me. So I'm Marcus. I'm the CEO of ForestHub, and we provide a platform where you can do agents for embedded and edge devices over the whole life cycle, build agents, deploy agents, orchestrate agents, and do agent ops over the air update, really the whole life cycle. And in this presentation or in this workshop, we want to talk a little bit about one use case really specific, the self-driving home. And with this example, I will show you what everything is important when you build agents and embedded devices, and how they can communicate, and how the architecture can look like when you have inhomogeneous devices in the field. And yeah, so let's jump into this. So first, a little bit about this topic. Smart homes are not really smart, to be honest, because normally when you have a smart home, you need to be smart, and to bring the smart rules you define to the smart home. So you define, okay, if it's over it's under 20 degree, then heating up. Is it over 30 degree, then cool down. If there's motion, make light on, and so on. So you need to be smart, and then you can provide this rules, your smart rules, into the smart home. But this is not really smart, and this is only rule-based programming most of the time. And I think the most here are programmers, so it's only some if and else, and that's it. It's not, yeah, it's limited. Say it this way. And when we want to try to bring the agents really in the home, we have a fully new perspective on how we can make smart home really smart. And in the normal, we have, for example, the sensor, then we have a rule, and then we have an action. Like I talked before, it's under 20 degree, then we have the rule, turn on the heat, and we do the action. And with the agentic system, we have now a different perspective on this field. So agents at all try to perception, they have context and memory, they have reasoning, they have different tools they can use in the normal, and then they can do an action and gets, in the best case, the feedback out of this action. So we have self-learning agents in the field. And so this is where the difference is. Before, we only had different rules, which are smart because you are smart or I am smart, but not because the algorithm is smart. And now with the agentic systems, we can really bring a little bit of smartness, a little bit of intelligence really inside this field. And yeah, let's talk a little bit more about agents. So it's fully, every one of us is really on one level. So a normal model, a normal LLM is not really an agent, because a model maps the input to an output, and that's all. So we really need to write an answer, or write something that we get an answer. And a script is not an agent too, because it's really fixed steps. And the chatbot, it's only produce words. But what we need is really an agent system where we can perceive sensor data, events, where we can reason, so we know what the goal is and what the context is. We can act with different types of tools, and we can observe, does this action work? Was it successful or was it not successful? And everything is always with a goal we have in mind for our agent. And when it comes from autonomous building, for example, we have a lot of different types of input and output. So the normal agent, like I said before, we have a goal, we have context, we have something like a planning system, we have tools, we have local memory, and then we can connect different types to these agents. We can connect sensors like camera, temperature, pH value when it comes for smart gardening, for example, microphones, buttons, and so on. And of course, we can provide other tools, which could be other AI models. For example, a vision model. We can give our agent a YOLO model, or an anomaly detection. And yeah, the small language model, of course, we need this for the agent. Then we have different types of actuators. We have pumps, we have lamps, fans, speakers, you name it. And when it comes then for the smart home, and then we really want to observe everything which happened in this home, we need have a structured observation. So what happened in which room, what happened with, what does every agent see, how does he act, and so on. And in the house, you can not only have one agent, you can have different types of agents, and then the agents need to discover themselves and ask the agents for help. For example, when one agent doesn't have the right tool, but he knows an agent who have the right tool, like humans. I don't have access to ST boards, but Danilo have access to ST boards, so he helped me to achieve this use case. And this concept we can bring to the agents too. And then the cloud service, which is optional in the best case, because when it comes to the use case smart home, I think you're with me. Even the hypest cloud engineer is with me. Your data, you don't want to have your data inside the cloud. When it comes for camera data in the building or in your room, you don't want to send them really out. The best case, and this is what I will show you here in the use case, is that the picture, the image data doesn't leave the device at all, not even in the home. In the home building, it's sent the data forth and back, and only the information we need. But I will go a little bit later on this. And then, of course, we have policies and we have feedback. We have permissions. For example, don't make the heat pump over 50 degrees because it will be too hot. 50 degrees Celsius. Yeah, because this will be too hot. And we have, for example, results, and we have learnings, and this is the policy and feedback. And all this together makes a good agent. Yes, so now a little bit to make the bridge about embedded agents or edge agents. So normally, most of the agents we know, they are running in the cloud, for example, a coding agent, or they live in big servers when we have big, large language models. And in this case, we only have, a kilobyte of RAM is maybe for the small AI models, but when it comes for small language models on device, we have, for example, only gigabyte of RAM, 1 or 2 or 3, and we need to make this happen. Then, of course, we need in the cloud the connection to the internet, to the cloud. We need the data in the cloud, the APIs, and so on. And when it comes to embedded agents, we have, of course, the benefit and the problem that we are fully offline, that we often have, for example, physical consequence, because when I control a heat pump, this is a physical device which can get overheated, or an AC which can get broken, or imagine a robot when we think a little bit further, or a clean dust robot. This is our physical devices which can broken or can harm any other things. And this is where the difference is often when we look at the normal cloud agents, which run, for example, in a company, or the embedded agents who move the real world. Yes. And now let's jump back to our smart home use case. So one home with many specific agents for different tasks. So, and this is how an architecture can look like in an inhomogeneous field. So in every room, we will have different types of devices, because I think this is pretty normal. We not always have the same device or the same connectivity in every room. So for example, you can imagine we have a camera in the kitchen where it's only an STM32N6, which is pretty well and pretty strong for classical machine learning algorithm, where you can run YOLO in real time, which is no problem. But it's not strong enough for example, language models. But then we have, for example, an edge gateway, which runs on the STM32 MP2, where we can really make language models calculation. So we can send the information from the kitchen agent, vision agent, what the agent sees there, to the gateway agent, let's say it this way, and he can can put his knowledge out of this information and can bring the context together and plan the actions for the vision agent. And this you can put in really every field. So for example, one agent for energy, where his goal is to reduce the energy. Then we have one agent for climate, which his goal is to have the perfect room climate in every room. And these goals are not aligned, because a perfect climate costs energy. The energy agent wants to reduce the energy, and so they need to talk to each other, and they need to make them better over the time and need to optimize themselves. And this is what you can do in a smart building when for energy consumption, for example. And so you can see, you can think this really, really big and have a lot of types of different agents. And of course, you need a policy agent too, which looks over all the other agents and is looking, okay, what they're doing. If this is this reasonable? Is this that what the user, that I and you, want in our building, or is it a little bit too much hallucination on this topic? Yeah, and therefore we don't share the raw intelligence. So we really need to put everything in a really good structure. And this is what I will jump a little bit deeper a little bit later. So we need to share information. And in the best case, we don't share the raw information. So for example, I don't want to send my image data in from one device to the other device. It should be staying as local as possible to make it even more secure. And but what I can send is, for example, context information. So my camera sees a mobile phone, which is placed in the kitchen table, for example, and this is the only information I want to need, or I want to see when I ask, oh, where's my mobile phone? And I don't need all the other information. I don't need the pixel data. This is not important for this use case, or for my goal as a user. My goal is to search my mobile phone. So I only need this information. Only this information should be sent over this network. And this you can do with different types of patterns, of course. For example, an agent, the different, so we have different types of cameras who define, okay, see, okay, here is Marcus, who recognize me and only say this information. Marcus is inside the living room, or the postman is coming, so everything is fine. This is not a security issue because I recognize this as a post office, but I don't need this image. I only need this information, postman. Yeah. And therefore, to make this all happen, it's we need a really strong architecture, which goes hand in hand, but have really defined task. And what the layer down under, of course, is the physical world and the sensor data, the sensor. So of course, cameras, temperature, pH, mics, buttons, pumps, as I told before. Then we have, of course, edge devices, which can collect this data, which can send this data, which can process this data, and so on. Then we have this agent on in these devices for vision, for file detection, gardening, voice, you name it. And then out of this high-level information, we need to communicate. This could be, for example, like a protocol, tiny A2A. I will explain a little bit more further. Then, of course, we have this sending lanes, this protocols like MQTT, HTTP, so the classical. Then the shared intelligence. So we want to have an policy system. So we need to save the states which are in this building, and then of course the operation system. So we need to monitor what the agents are doing, logging, tracing, deployment updates, everything who makes not to build only an agent in 5 minutes. Everybody can do this with Cloud Code, but to make an agent really, really stable in the production mode. Yes, and if you want to have this, you can put a cloud connection, of course, to make fleet-wide learning, long-term analytics, and so on. And yeah, now let's jump into the use cases. So, and I will show you now live, afterwards live, how this can look like and really on the ST hardware. And when normally, or in the smart home, what we want to have, we want to observe and remember things. For example, if I let down my mobile phone in the kitchen, I want that this is remembered where the last position of my mobile phone was. Or for example, my wife really likes dark light, so it's not that shiny, and I like when the room is really lightful. And I want that the agent system, when I come, or the smart home, when I come into a room and it's me, I want that it's really bright and everything is full of light. But when my wife comes, it should be remember, okay, my wife likes it's a little bit more dark, not that bright, and this should be remember. And of course, it should know about hierarchy. So if me and my wife is in the room, then the rule of my wife is the right one and not mine. And this is what I want that the agent system is doing. So observe and remember. And then, yeah, I have, of course, targets. For example, where's my mobile phone? I have targets, reduce the energy, and so on. It should detect, coordinate the other agents, talk to other agents, how to pick up the target, the goal, optimize everything. If after an action, for example, and operate the whole fleet, so monitor, audit trail, and update. And yeah, now a small deep dive into tiny A2A and how such a communication can look really efficient. Maybe, well, I'm pretty sure that most of you are an expert in agents, and you already heard about A2A, agent-to-agent protocol. And when it comes for embedded devices, and you're an expert in this field too, you know, communication is always really heavy to do. When it comes for small devices, communication is always expensive in energy, in calculation effort, and you name it. And therefore, we developed a tiny A2A agent-to-agent protocol where we define the protocol a little bit slimmer than the normal one. So we have really the intent, like the normal A2A. So what is the goal of this agent? What he saw, for example, what does he recognize, and where does he need help? Which methods he has, which tools he have, which is the owner of this agent, or which where this goal comes from me or my wife or whoever. And all this information is more compact than the classical agent-to-agent protocol, because we limit it really for the use cases. And then you can see that it's a little bit smaller, a little bit more concrete when it comes for the sense of this intent, for the how agents can find them, how they can communicate to each other, how to give them the intent with them. So we only give the smallest amount of information, and the other context information is inside of this multi-agent system. Yes, and now let's jump into this use case. So this is now running. I need to share that for my. This is running here on the STM, on two different types of STMs. So one STM32 MP2 and one STM N6, which has not the capabilities. And now you can see the N6 is on the mobile phone I search, and the other one you can see me. Hi. And for example, if I have a question, what do you see? And this is what I told you before. Now we can send one order to all these agents. For example, what do you see? And now the agents want to solve my problem. So the agent on the agent register this order. Then he looks, okay, which tools does I have? He sees I have a camera as a tool, and I have a YOLO model as a tool. And now he takes this order, he capture an image, he bring it to the give it to the YOLO model, gives the takes the output of the YOLO model and give it back to me, because this was what I wanted to know. And now you can see that the agents gives me back. I see a cell phone, which I showed you before in the image, and then the other one sees a bowl, and he sees the handbag from my wife, and it sees me. And yeah, this is how the agents can communicate over a whole network. And what is really interesting is that the SLM is only on one device, and the other devices capture or give the information to this SLM and give it back to the smaller devices. So as long as you have in the smart home one device which is big enough to calculate everything, every other device can participate out of this calculation power. Yeah, so the other use case is the detection fall, and this is here I need to fake the image data. So now you will see in small use case where I now stream the image data to the STM, and he recognize everything what is happening and makes the action in this case. So imagine we have here a small use case, elderly care, and a person comes inside of this room. So the agent sees, okay, someone is here, everything is fine, no problem. Then we have, for example, a case, the elderly person falls down. So this gets recognized, the fall gets recognized, and the person recovered. So everything is fine. Of course, there wasn't fall. This was recognized with pretty well accuracy, and but it's working out good because there was no problem in any case, because he stands up. And now we have the problem, or now we have the case, for example, the elderly person falls down and stays on the ground. Like you can see, he is not coming up, and this gets recognized. This gets recognized by the post model and by this agent, and then he asks, is there any problem? There is no response, and then he wait, of course, a couple of seconds if there's no answer, and then he make an emergency call, for example, if he had the connection to the telephone, and then he, for example, unlock the door, because he have this tool to unlock the door, so the emergency person can come inside and rescue this person. And this is how you can make smart home not only for comfort reason, even more the agents can help you for security or for secureness reasons. And yeah, this with only a couple of really basic models, which gets interpreted by an AI agent and really know what to do with this information, what you normally need to train big networks and need to train or write a lot of hard algorithm or good algorithm to detect the fall. And now we can say, here's only this post detection. Have a look, is this person laying on the ground? Is it falling down? And so on. So the interpretation of this post model gets directly from this get directed from the language model or the agent itself. Yeah, and this everything what you saw was running on the MP2 here in the room. I streamed the data directly there, and it was really fast when it comes for the pose detection model, which runs super fast on the STM device. And the language model, of course, is not that fast because they're a little bit bigger, but and so you can really cut the calculation effort. So you make the models on the embedded device who runs really fast, more than real time, as YOLO, as post detection, and so on, as normal model, and then you can put a bigger model, the SLM, which interprets this information, and so you get really good results for this case, or for different types of cases. Yeah, of course you can think even more and make this bigger. If you see, will have a look on my LinkedIn, you will see an image where I say just try to make a gardening agent. So there was a hydroponic tower where I said, okay, here you have all the information: pH value, temperature, how much ingredients are in the water, and everything, and of course energy, because I want to save the energy, and do the best you can put on camera how the salad is growing, and the agent can interpret all this context information and make the best out of it. Yes, and and when you really capture everything which happened in the house and everything is fully local, you can then have this interpretation layer, which I think it's really powerful because it learns your behavior. It learns how you move in the house, how you really want that your house is behaving, adapted to you. If my house knows I'm to work from 8 o'clock to 5 p.m., then it can reduce the heat over this time. And when it knows, okay, every Saturday at 18 o'clock, I have my electrical car. I need my electrical car because I don't know, I go to the cinema. Then it's recharged my car really for this point, and in the other time he can sell, for example, the energy out of the car with bidirectional charging and so on. So you can think a lot of different types of use cases when my house is really thinking for me. Yes, and now the last chapter. Yes, I'm in time. I need to hurry up a little bit. Is you see now a lot of futuristic thinking, how smart home is doing, how agents can communicate, which protocols, and how this can work together on really small devices also. And now let's have a look on really production mode. So and really see what is really important for making agents. To build an agent, I always say this to our customers, to build an agent on an embedded device, 5 minutes in cloud code, and everybody can do this. But this is not enterprise ready. This is not what you, when you make a product, want to have, because you want that it's stable, that it's safe, and that it runs really good. And therefore, you need agent ops. You really need to capture every event of this agent. And the good thing is, agents are computer software. They are not humans, so we can really control every step, and we should control every step. Why is he doing what? What is he doing? How long is he doing something? And really everything. So we can see how the communication is going, how this action is going, and evaluate the agent all the time. And this is what we really need to do with the agent ops. And it's even more important when it comes for use case in the physical world. We don't want that the heating pump is going over 60 degrees because I don't know, one sensor is broken, and we need to see this. We need to recognize this, and the agent ops need to recognize this. With, for example, in policy agent, which runs out of this. And autonomous doesn't mean uncontrolled. So when one agent, for example, say, okay, let's activate the ventilation, we can ask another agent, is this correct? Is this successful? Is this a good way? Or if we want to make this action, we can control this action. Was the ventilation really, does it really go on? Or is this was this order going into nowhere? And so we really need to capture everything, what has happened, the reason, the request, approved by, executed by, model version, agent version, and so on, and you name it. And this is what an agent system really make it powerful and enterprise ready, not only a small cool gimmick I developed in a couple of minutes, so to make it really meaningful and really enterprise ready. And therefore, of course, you need a platform. You need to have a process to make this, for example, sign in and check, package signed, compatibility verified, and we deploy, for example, on one device. Then we deploy to different only for one device and test it, make a health check, then register to other agents, compare the matrices, and then we can do a fleet rollout and, of course, roll back if there is any error. Because the behavior, when you change the SLM, the behavior will change. And yeah, I'm a big fan, and I think the most of you guys are a big fan to calculate the data where it's coming from. So, for example, on a small MCU like the ST32 and 6, we can make sensor pre-processing. We can simple object detection, anomaly detection, actuator control, which is we can do on this device pretty well because it's strong enough for this. And then on the more edge gateway, for example, MP2, we can make larger vision models. We can local language. We can event aggregation. So have a bigger view of, okay, what is happening in this whole building. And then optional, of course, we can do this, bring this in the cloud or even higher devices. I think you get the concept. And yeah, here as a small, what I told you a lot before is here the small architecture for the ST32 and 6. Here was a small YOLO Nano on this MPU, which works really, really fast. And on the MP2, we have the small language model, and they communicate only with this structured data and not with this unstructured image. So to really have data there where it is. If you want to build this use cases for yourself, I will provide or in the tomorrow, I think tomorrow we will update our GitHub. I will send the link inside the chat, and then you can have these demo cases on our open source platform, and you can try them by yourself. When you have an N6 or an MP2 at home, you can see how this agent can communicate over your home Wi-Fi or your home network, and with all this data stored locally and not send it anywhere. And yeah, to try to rebuild this use case, I think this is super interesting to learn about embedded agents and the capabilities of them and how they behavior. But I will send this GitHub link, and give me one day to publish everything, because we will have a big update tomorrow, and then the demo case will come with this bigger update. And yeah, of course, this idea I showed you, you can not only bring from the smart home use case, you can provide this to other fields, the industrial fields, in the marine field, and wherever you can, wherever you think an agent should be not inside the cloud, it should be local, because you don't have an interconnection, or you shouldn't have an interconnection like the smart home. Then you can take this idea of the embedded agent and bring it anywhere. Yeah, three small things. I know this was a lot I told you in this workshop, but embedded intelligence is becoming agentic. I think we see this in the great talk before, which was really, really interesting, that it's the intelligence come really to small devices. Then multi-agent systems need shared memory, so they can communicate to each other. They can handle your problems, your goals together, and production requires a good agent ops. And agent ops on embedded devices, it's not that easy like in the cloud, because in the cloud everything is running on one platform. When it comes for embedded devices, they have sometimes in connection, sometimes not. They need to bring the data inside somewhere where you can do the agent ops. So this is not that easy, but this is really important for good use case, for strong and stable use case. Yeah, if you have an idea on a use case, feel free to reach out if you want to have a chat. we can have a chat together about different types of use case. Feel free to reach out about this specific use case or different other architectures. Yeah, feel free. And thank you very much for your time. I hope I'm in time, but I should be. And yeah, thank you very much for your attention. And if you have any question, please feel free to ask them.
Marcus, thanks so much. I mean, it was a really brilliant workshop. What you had. A couple of questions. So you said that tomorrow the repository link will be available because there was Andrea asking. Okay, very good. And there was another question. Do you see a possibility of the edge agents collectively entering a non-controlled home situation? Shouldn't be a central agent to make sure the home is under control. What is your view on that, Marcus?
Yes, indeed. This is a really important task everywhere where you handle real world, what we are all loving to do because we are embedded engineers. It's always good to have one central agent, one policy agent who have a look up over all this communication, what is going on. So because you have a decentral architecture in a multi-agent case, one agent should have a look on all this communication and maybe says or make it as a gateway. For example, it need to be controlled by an agent, or he can or he can see in a communication say, okay, don't do this action. This will be not good, for example. So yes, indeed, have a central agent when it comes to smart home. And I think this will be the direction the smart home developers will need to go when it comes for agentic home.
Okay. Very good. And I think what you brought here today, compared to my experience with smart camera at home, is really a quantum leap. I have cameras at home, but by far are not comparable what you are proposing. So, in your opinion, Marcus, call for action. What do you want the community to do tomorrow morning, following what you just spoke about and demonstrated?
Think about good use case in your environment. Agile Foundation is a lot of developer community. Here, a lot of developers, and we all loving do our cool AI, TinyML stuff, Edge AI stuff. But the agentic use case can go a step further, can make even cooler use case, like I showed you in smart home, or in other industries, we can optimize. Systems can now optimize themselves. You can have agents on a machine which can build models on the fly, machine learning on the fly if you need this, for example. So really think about use case in your field to make your product even cooler with agentic embedded agents on the device. And yeah, this is my call to action. And if you need help, reach out. No problem. I am happy to help there in this point, but I think we need more cool use case really for agentic edge devices.
Fantastic, Marcus. Thanks a lot to stay within your slot. You saved also some time. Excellent. Let's continue to work together. I think it was really comprehensive and also informative, the use cases that you shown combining STM32N6, which is a TinyML type of processors, and edge generative edge AI through the STM32MP2. So that's brilliant, and thanks. Let's continue to work together. And very much appreciated your availability to hold the workshop today.
Thank you very much for having me, and thank you very much for the cooperation here. Really, thank you. This is, I think, like I told, when the people with ideas coming together, even better and bigger ideas will come out.
That's a strong message for the whole working group, Marcus. I'm really glad you just said, because great things come on the table when people cooperate. Yes, that's the whole point. Thank you so much to having said. Very good. I leave you, Marcus, and next is Andrea Basso. Please come on video, Andrea.
Hi, everyone.
Ciao, Andrea. So, a few words also with you, Andrea. First of all, Andrea Basso is I don't see you on camera, Andrea.
No, I see myself on the.
You see yourself.
Yes.
I see you black.
No, I see me fine.
Okay, but maybe it's just me. Maybe Rosina, you can cross-check, please. So a few words about Andrea. Andrea Basso is a huge expert with a lot of experiences in many breakthrough fields coming from starting from multimedia signal processing to the artificial intelligence and to generative AI. So what I really like about what you will hear from Andrea is that he designed, engineered a camera which doesn't need anymore your prompts, and that simplify the user experience, still retaining both TinyML type of features and generative AI. So the workshop is grounded video understanding on the edge with small language models. And please, Andrea, the floor is yours.
Great. Let me share the screen and see if you can see everything. Can you see?
Now I see you in the background.
Very good. Okay,
yes,
good.
and I see the screen.
Let me close this window, and then I simply will trust you because I cannot see the video. Is Anthony also joining? Well, first of all, while Anthony is joining us, I want to thank Danilo because it's always a source of inspiration, and this project actually is one of these inspirations. I remember we're talking about N6 and object detection, and at a certain point he said, "Yeah, but what about the MP2?" And I said, "Yeah, what about the MP2?" And so that started, a lot of activity. And the first was, to optimize Llama CPP for the MP2, trying to use OpenCL, try to use the MPU, and then seeing what YOLO would do on that device. And so at the end I said, you know what? Let's take this as a challenge. How much intelligence we can put on this device? And so these are how the narrative camera actually started. So I hope Anthony is also on because I cannot see you. Let's see. No, I cannot see you. And so we said, okay, the idea, the challenge is to get this device and to implement a smart camera, but really smart in the sense that it would get the image and then provide a description of what the camera is seeing. And so you can consider that these are quite tough task because you need to get the image, then probably you can do object detection, segmentation, and so you get the bounding box. But out of that, to go to a natural description of scene and actions inside the scene, it's a big step. So the first idea said, okay, you know what? We take the camera, we do some object detection, and then we can use a small language model optimized so that it can it can, use whatever object has been detected to try to guess what, what the room is, what the environment is. But that was really coarse, wasn't, and also wasn't challenging enough, simply because, I was talking to Danilo, we were able to, optimize Llama CPP for this board already, being able to get, tens of tokens out of it. So I said, let's go full power. Let's see if we can stick also a vision model inside the board, and what happens when when we do, so that we can really describe the scene. And so this was quite challenging, because a small language model, the detection, and visual language model on the same board, considering that is a very somehow limited board that I love, because the processor simply, there is no heat. It does all this processing. It's on since this morning, and practically it's cold. Because it's very, very, very power efficient. But so we picked the challenge, and so we start designing, what the board should do. Anthony, are you on?
Yes, I'm on. Hello, everyone.
Let me introduce Anthony. Anthony is a good friend. We met many years ago. He's an expert in AR and XR. Is a very well-known blogger. But now it's extending his domain of interest also to Edge AI. And so we met recently, and I said, look, I'm working on this. And he said, you know what? Yes, I also got quite a bit of hardware for doing, fine tuning. And then I said, look, let's see if we can work together. And so this is how the collaboration started. And he will talk a bit about the fine tuning that we start doing on this board. So coming back to the components that we thought we wanted to have on this board. Of course, all the acquisition part, and actually the board, the STM32MP2, has a nice VPU and a nice ISP, image processing engine, and VPU video processing unit that allow to do hardware encoding and decoding. So that I think is great. We can use it. And has also an NPU, has a Vivant NPU, 1.35 tops. And so I said, you know what? If we want to describe the image decently, I guess we need to get a decent resolution that is, at least 640 by 640, and with optimization without too much effort, because there is a lot of literature actually how to get optimized YOLO A10 on the board. We got it running. Actually, to be honest, we went a bit further than that. We ported also YOLO E, YOLO everything with 736 classes, but it's not the topic of the talk today. And it's way more powerful in terms of recognition objects. Here we're gonna limit it to Coco 80 as a scenario. And then, of course, we said now we have the bounding box. We can get them, at a good frame rate. But these small language models and visual language models typically, hallucinate like crazy if you don't drive them properly. And in addition to that, having multiple entities running on the board, we had a bit less than 4 gigabytes. It's challenging because these engines require memory to run properly. So we did some experiments, and then we had a few reflections and thought about how to optimize the process. First of all, we really had to I'm just jumping a bit in advance because I think I already talk about this. For the small language model, we tried a few of them. We tried Gemma 3, 270 million parameters. It was using too much memory, and said no, we need to go to something smaller. So we really focused on small M2 at 135 million parameters because it was fast. It was also somehow relatively not so much memory hungry. And so I said, you know what, if we want to be fast enough, we can actually have a local server on the board that is always ready to go, so we don't have the warm-up timing, so that we can call it at high frame rate. Of course, for having the small language model working properly, you really need to do quite a bit of prompt engineering here, and also context.
Andrea, sorry to interrupt you. You're not sharing your screen anymore.
Really? Okay.
Yes.
Let me go back.
In the meanwhile, let me tell that it's really crazy what you're trying to do on this board. That's why I also joined the project. And also I love that since it's everything running locally, it's very privacy oriented. And also since the system, I guess, can also be used like in security scenarios where, safety, anti-tampering, etc. is very important. Okay. The fact that it's so local is fantastic. So that's very important for this project.
Okay, and, can you see it again?
Wait a second. Hola. Yes, you are live again.
Okay, very good. So I put this here. This is the demo. I'm going to show you it later. Okay, so that's that was challenging, but mainly we wanted the capability of generating an inference every 3-4 seconds. As I was saying, prompt engineering and context engineering was essential here because we wanted to keep the context as small as possible for two reasons. One, to reduce the amount of processing that we needed to do here, because of course all the self-attention is related to the amount of memory and the amount of context that you are using, as well as the output. We wanted really to limit the number of tokens used for the output to avoid speculative behavior of our very small language model. So we did that, and a lot of effort went in designing the proper environment for the small language model. But having said that, we had another challenge. We said, okay, we want to run a vision language model, which is kind of crazy, but it is possible because we actually did it. Now, for example, small VLM2, that is, our selection, is practically the smallest, one of the smallest visual language models available today, was working on, quite large tiles, so 512 pixels tiles that definitely give the best performance in the kind of analysis that they can do of the images. But on the board was taking like 75 to 80 seconds for processing. So I said, well, you know what? We can use that, but we need to really use it with quite a bit of parsimony and attention, because every time we run that, you need to wait more than a minute to get that. So what we did, well, the first thing I did was saying, okay, I'm trying to push this to the NPU. We did all the mapping, starting from all the instructions and the NPU was providing, but at the end it was way slower than the CPU for a lot of swapping that actually was happening through the NPU and the CPU and the board. So we had to leave that path and then think on how we could optimize, what we had. And so I said, well, first of all, we compile Llama CPP in a very, very efficient way. And you will find this at the repository. You need to really fine-tune Llama CPP for the A35 and also be a bit more aggressive on the math side and optimize the code. And actually on the repository, you find the binary already there. But then I said, but what about if we modify Llama CPP, and in particular the projectors that instead of using big tiles like 512 by 512, use smaller tiles? Because while we were doing that, I had this idea. I said, well, once we somehow have an idea on what the scene is, then we can compute the region of interest that in general is smaller than the overall picture. Is where the focus is. And if that is a smaller image, maybe we can use smaller tiles. Is exactly what we did. So in a quite audacious way, we went and modified Llama CPP. The patch is actually on the repository, so you can modify the original code according to what I'm saying. And of course, as we did for the small language model, we need to be very careful on how to do prompting. So there was quite a bit of prompt engineering and context engineering here, because that is something that somehow influenced quite a bit the speed that the VLM can have. But then another problem came out. Now, the detector is detecting some things, but not everything, right? And the VLM instead is detecting other stuff in the image. So how we can manage that thing? So how we can reconcile these two things? And the idea is relatively simple. We put all together and we cross-check if there are contradiction between what the detector has identified, what the VLM has identified, and we go for the most probable scenario. And you will see this in the demo. You will see, I will show you examples in which the green objects are identified by the detector. The orange boxes actually come from the visual language model. And when the context actually becomes richer in this way, you see that the system can converge much faster, because finally understand what is in the scene and can give a decent description. Of course, in addition to all this, we need to have a layer that decides when it's worth actually running the VLM and with which resolution, because I may be in a situation which I cannot really understand what is happening, and then maybe I run a full frame, or instead I really have identified a decent region of interest. Of course, the region of interest need to be of a given size, because it's too small, probably is not meaningful. But I can immediately switch to a smaller tile size, and so be faster in the response. Now, if we have also the capability of running this smaller tile size, typically 384, there is another issue. If I need to actually start another VLM with a smaller tile, and unfortunately I have to do it, I have two issues. First of all, I have a warm-up time that I don't want to have, because at this point I run the the full full tile size on the image, and doesn't make sense. And the other, it's even more challenging, management of the available memory. Again, we have 3.7 gigabyte of RAM and need to suffice for everything. Well, actually, we run two VLMs. The one that is smaller because the file is considerably smaller with respect to the full tile. The MM file is smaller, but we really need to play. We had to play very carefully all the memory allocations so that everything could stay in memory, so that we didn't need to restart any server, and the thing was responsive. In addition to that, of course, these small language models tend to hallucinate anyway. So we really studied a way of managing all this hallucination, mainly introducing some standard physical rules that would eliminate some inferences that wouldn't make sense in the cluster, as well as a temporal and spatial memory. So if an object appears in a given location for some amount of time, then we have a decay function that reduces the probability that that object is still there, but doesn't go zero immediately. Same thing when we do a scene detection, and we are able to nail down which kind of environment it is. I don't know, a classroom. Then it cannot be that at the next frame it says unknown. I don't know where I am. So we introduce these very simple notions, physical relationship that need to be true, on which us as a human rely on. And so all the actions and all the scenes are filtered through this plausibility, temporal and spatial filters. Of course, also implemented in a pretty fast way, just to make sure that the thing was responsive enough. If just not be happy to put code on this poor board, we said, okay, I don't have a display, so you know what, we need to have a web interface that is actually showing us what is happening. And so the board actually has an interface that runs on port 8080 that can show us exactly what's happening. So it's showing the region of interest, it's showing the detection from the detector, is showing the detection from the visual language models, and also the inferences and how they are articulated. And now I leave the floor to Anthony, that will tell you a bit more about the fine-tuning work that we started just a week ago.
Well, thanks, Andrea. So basically, this project is constantly evolving, and I started collaborating with Andrea in trying to fine-tune this small VLM. And the fine-tuning happened with a traditional way of doing that. And the first thing to do is finding good data to do the fine-tuning. So we evaluated a few public data sets, and we realized that at the moment the best we found is something V2 by Qualcomm. And the reason is that it's a very rich data set. All the videos are pretty consistent. They all regard an action with some objects and shot with the same format, etc., etc. And there's very good labeling related to actions that are happening, because the purpose of this camera is, of course, understanding what's happening in the scene. So all these videos have a clear labeling of the action that is happening. So it's ideal for what we want to do. So the videos are a lot, like 22,000 or something like that. So we filtered away the ones not having the Coco objects from the Coco 80 dataset, or the videos not shot indoor, or something that is we think is not compatible with the purpose of this project. And then we took, since there were still a lot of videos, we took a few of them, let's say with regular intervals, because the problem is that in this data set, like there are 100 consecutive videos about an object pushing another. So to try to add some variety about the actions, we had to not take the, I don't know, 500 consecutive videos, but just take random sampling the videos in the dataset. After that, since the videos are very small and just related to the action, we just can take just all the frames with some sampling, like regular sampling, 1 for every second of the video, and take the label that Qualcomm already provided, which is very good, which usually in the format something, does some action on something. And then we started around 1,500 frames, which seemed enough to do a first fine-tuning experimentation, and use the classical LoRa fine-tuning methodology with the Hugging Face library using Python. Created this merged fine-tuned model, and I use Llama CPP to do some sort of GGUF conversion, because Llama CPP can only run models in this format. So we used a very powerful dial workstation to do the fine-tuning, so it didn't take too much time to do that, around 15-20 minutes. But of course, something to remember, even if your machine is very powerful, the model should be run on the final small board. So you have to remember to do all the proper quantization and
Anthony, we were on Telegram, and he was pushing me these fine-tuned models, and when I was running them, it was like taking 5 times the baseline. So we had to spend quite a bit of time understanding what the heck was happening, and then we finally discovered that it was optimizing for an RTX Pro 6000, and not for our poor CPU based processing. So after having understood that, we're able to start running these models, and still they require optimization yet. Go ahead.
So and the next slide, we can see some early results. So these are validation images, by the way, not training images. So we can really see if the model is working. And I say it's promising because, like in the image on the left, the stock model sees nonsense, sees a plastic cup with a lid and blah, 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 but that's not true at all. While the fine-tuned model understands that's really a glass bottle that is put upside down. And that was really the label of this video, even if the video was never seen by the VLM. So that was really validating the fine-tuning was doing something good. But still, there is still a lot of work to do. And one of the reasons is that this the something dataset is very focused on actions. So now the VLM is finding actions even when there are none. And for instance, in the image on the right, there is a guy just holding a cup in front of a fan. Tries to find something like, he's putting the cup somewhere, moving it away, because it's so used to finding actions everywhere that it needs to find a movement somewhere happening. So even if the first results are promising, we still have to work in improving how we do the fine-tuning to try to avoid these, let's say, hallucinations. But I think we are on the right path to do that. So back to Andrea for continuing the narration.
Thank you, Anthony. Okay, so I have actually the board here on my side. I took a picture. As you see, it's connected through Ethernet because it goes faster as a camera, and we're gonna see it in a second. This is the repository, and we're gonna navigate it together now. So let me just open up the repository so that I can guide you a bit there. This is the repository. Here you see we have the binary files, what you need to run the SLM, and this is instead for the VLM component. Then these are the files that allow you to first of all, modify the Llama CPP to support different variable size tiles. And again, you need to use exactly the version that I I use for that. That is the B8724, and is recent. It's of June 12, so it's a bit a month ago. It's true that updates on Llama CPP happen daily. So, and then the second thing that you need to do is to get the original projector files, and you can get from Hugging Face, and then once you patch and recompile Llama CPP, you can do this directly on the board. What you can do here, there is you see a patch mmproj.py, that is the file that will modify the mproj file that you downloaded from Hugging Face with the different tile size. And I experimented with 448, 384, and 256. 256 is definitely the fastest, but is also the one that gives less quality. 384 seems to be a good, a good compromise. Here you can actually, verify. It's one of the options for this patch to verify that you did a good job in the conversion. Of course, the file that you get from Hugging Face are F16, and here, we need to quantize them. So the quantization is Q8, the one that we have used, and for this you can use Llama Quantize, and that is in the package from Llama CPP. You cut really the size of the projector file to 160 megabytes to around 80, and it still provides good performance. I tried the Q4, but it really the quality degenerates a bit. And this is some test that we run with different tile size. As you see, the 256 is definitely the fastest one. Here, there are README files for everything, so with all the details, so you should be able to replicate everything pretty well. Here in the models, I just left the YOLO 8 Nano 640 by 640, because this is what works relatively well. As I said, we ported also YOLO E, but is way more complicated to explain, how to port that on the MP2, but is definitely way more powerful with 736 classes. It is something that gives quite a bit of power to the overall system. I didn't include the video because we have a 100 megabytes limit on GitHub, but it's you can get videos from Pexel that are free to download. If you have videos, you can directly use them with an option from the deploy.sh or run also. And here is all the documentation for the workshop. So the README here, mainly it's how I articulated. The first part is really how you patch, build, and quantize Llama CPP, step by step, that we already saw. And I also put two small pieces of Python code that allow you to play with different parameters. So the number of threads, typically 1 or 2. Here you have 2 cores. So and the context size, batch size, and micro batch size. And of course no warm up. But these allow you to play both with the VLM, the optimized VLM, and the optimized SLM, to see the kind of performances that you can get. And the final part of the workshop is actually see these things working, that we're gonna do in a second, and just gonna go and show you what what we have in the repository. There is all the Python code for the capture part that drives the live camera, but also drives the file the file management. It can get the system can get files from your PC directly from the web interface, or from the board, which is faster. There is a configuration file which is quite long. I put some comments in inside. There should be self-explaining. We talked about the region of interest. We talked about the region of interest for the VLM, how it's managed, all the parameters that drive the small language model, and some of the parameters that relate to the image. These actually are not used in this version, because there is no code that does the image enhancement, and then all the logging that is always extremely useful. I can tell you that if you want to find bugs, and then all the information related to the streaming part. So how the video get to the UI. You can imagine that there are quite a bit of tricks inside the code. Both the VLM and the SLM, they have a cache internally, so that when possible there is no re-encoding from the VLM side. There is no re-encoding even from the detection side. Demo.py is the main piece of code that drives the demo. It's a lot of code, so here we are talking about just this is 2,100 lines. But all the other are not much smaller. Just to give an idea, it's overall it's I didn't count all the code that we have, but I think we are talking about a few thousands, a bit less than 10,000 lines of Python code. There is a requirement file that will help you in installing on the board whatever is requested, and then the server part that manages the motion JPEG server and all the UI. So this is all the code that I have to admit Claude was a great friend for this, because if I had to write it everything by hand, the interface, that would be a headache. And then again, there is deploy that allow you this file that allow you to have the code on your PC or Mac, maybe on VS Code, and then transfer it directly to the board. In fact, you see here the board is root when you log in, and here I've connected to 192.168.7.3. because I created a direct link through a USB-C to Ethernet connection. So it is fixed. Having said that, I think it's time to run some demos. Anthony, I'm still sharing, right?
Yeah. Just maybe if you can make full screen so people can see it better.
Full screen.
No, just if you want to maximize it a bit, a window, if you think it's better.
Okay. Let me see if there is anything else I want to say about the slides. No, I mean it's mainly what was put in the was put on the repository. So I think I can close that, and I can make this bigger.
Yes.
Okay, and now, without further ado, let's see if this thing works. Okay, so let me, I already loaded the file, but let me do it again. This is a file that is on the board. Actually, you know what? Let me rerun it completely. So I'm really doing a deploy here, so that we got fresh, and you see also the live camera. Pam pam pam. Transfer all the code. Now I do this. Okay, it's starting, and very likely you're gonna see my face in my kitchen. Oh, here we go. That is the camera, and you see the kitchen is doing all the recognition, and so it's working. Actually, you see, start detecting and understanding where we are. So it works, but just for practical reason, we're gonna use files because it will be way more complicated to run it this way. Okay, so we start from this scene that I think Danilo already saw several times with all the improvements that we got out of this. And you see the interface. This is the video. We're gonna see everything showing up, and I can select what I enable here. So let's enable the detection and the small language model just to understand what this thing can do. So if I push play, this thing should start. Okay, so you see it's actually loading the SML, the small language model. It is starting. You see the region of interest get computed in real time, and all the different objects show up. Okay, so this, you see my mouse, no? So this is the detection. So all the objects with the probability of the class have been detected. This is actually the classification coming from the SLM, and you already see this is that at a certain point should say kitchen, but it's already understanding, with the rules that he has inside, that the action is cutting or chopping. It detects one or two knives, and then also the potted plant, the environment. So it is likely that once we enable the VLM, it will detect that this is a kitchen. Okay, so let's stop and let's start again. And so I enable the visual language model. So everything runs. There are 3 components running on the board, believe it or not. The detection and 3 language models, 2 visual and one small language model. And I cross my finger. I hope it's going to work. Yeah, stop. No, I need to push play. And so let's see. Tac. Now the small language. Oh, good. Look at that. And it was really quick. It took 4 seconds. And it was able to detect the environment that is a kitchen. Very good. And also, the SLM is saying, oh, there is a person and is cutting or chopping something, but it cannot really disambiguate that, also because cocoa doesn't have the yellow pepper over there, has lemons, oranges. And actually here, the resolution is not high enough. It wasn't able to detect that. Now, given that the SLM wasn't able to really good a good description, the different rules and the gating that run inside the board decided to run a full frame VLM. And you see in the VLM description, this is a synthesis that uses the information from the scene classification. So it's a kitchen, and there are 2 balls, a person, a potted plant, but is doing further analysis. And at this point, Anthony, we need to talk. Oh, no, look at that. It was really fast. So you see, so he detected, but he said, yeah, she's cutting a lemon. 50% of the time it gives bell pepper, and we are simply not lucky enough here. And unfortunately, that won't be corrected later on, because it stays, and there are it happens rarely that the VLM actually recognize the bell pepper, and need to run a full frame for that. Here you see it's running on the region of interest, so it's using the smaller, tile, so 384, with the third server, the third VLM. But you will see that along all the analysis, mainly it will stay the same. So it's it won't be able to clear that unless we force another VLM full frame. You can play a lot of that, because, as I said, there is a context engineering side, there is a prompt engineering side, and also there is a resolution side. If you run everything at 512, you can get better performance. Now let me show another example. Let's take this one, in which the detector is not doing an incredible job, and the VLM actually is helping. So let me load this. Okay, here we have the tomato. We run both of them, I will say. Now I click play, and hopefully this works. You see he's making a mistake. He finds an orange and an apple, I think, in the detection. And you see it detects that it's a kitchen, because it's there is a bowl, the environment looks like a kitchen, but it cannot tell really too much about the scene, and it says I detect that there is a person, and the person is sitting at the counter looking at a plate of food, and that is the most reasonable thing that the SLM is able to spit out of this image. And you see the input that we give to the VLM. It's the scene appears to be a kitchen with an apple and orange. That is wrong, because it's actually a single tomato, and so things are not the best one. Let's see what the VLM does. Typically, the VLM here recognizes the tomato, so it should change color at this point. And once the scene becomes a bit more coherent, then it will be able to give a better description. I'm looking for this orange box that I haven't seen. Okay, no, simply it didn't go as I was hoping. It's a person and they're cooking. It identified the knife, but I would say 90% of the time this gives there are tomatoes on the whiteboard. What we can try to do is rerun it, just to see if we can get this the demo effect, right?
Yeah, we tried it before the speech and it worked perfectly.
Yeah, it was perfectly right. But also, these are statistical methods. Mainly what we are trying to do is just put guardrails and to put as much known knowledge inside to be able to run in such constrained environment. But let's see. Let's try it again. I think we still have time, right? So, well, it detected the environment. It's a kitchen. That is good. And let's see if otherwise I have another example that will show you this orange orange box and reconciliation between VLM and SLM. So I think we need to talk. It's 70 seconds.
But by the way, how much is the cost of the board, since you're working on this limited hardware?
It's really cheap, for what is offering. I love this board because first of all, he has a lot of very, very interesting components. In particular, all the ISP, all the encoder and decoder is pretty good, and it's very flexible. There is also an M33 that I wasn't able to use, and I don't know if there is a way. No, so simply we need to accept that this time didn't go as we are hoping. I'm gonna show you another example in which this orange box should hopefully work. Let me again select these. Okay, so this is a classroom. The system will have difficulties understanding what the scene is. In fact, it tells me it's unknown. I don't have elements because it's 2 chairs and 1 person. It cannot disambiguate. And so it says, okay, let me run a full frame on this and see if we can do better. And so again, Anthony, we need to talk.
Well, I think that the classroom example is great because it's really, I think, the context where you don't want your data to go to the cloud, where you don't know what's
right.
going to
happen. Yeah, of course. Yeah, I forgot to mention. You're right. And actually, maybe you can say something about your experience, Anthony, if you want to say something.
Yeah, it's fun that like a couple of months ago there was a bit of a scandal with Ray-Ban Meta glasses that are connected with the Meta AI, and certain point a Swedish magazine realized that all these videos sent to the AI there was a manual review from humans, from people like in Nigeria, that were able to see like videos containing credit cards, numbers, naked people, etc., without the people knowing. So when your videos go to the cloud, you never know what's going to happen on the other side.
Okay, yeah. I have to interrupt. Here we go. You see the orange box that comes from the BLM. So he found a book, and actually there are more than a book, and that somehow it's definitely helping in defining better what the environment is. And if everything goes well, he will be able to say that this is a classroom and there is a young man standing in front of a table and with a book on it. So it's already got the last part. A man is standing in front of a table with a book on it, and let's see if it is also able to disambiguate the environment that should be a classroom. Of course, there is always the demo effect because we tested these, starting from this morning, and everything was going extremely well. But as I said, these are statistical methods, no? So the system does not understand the semantic of the room, understands the statistical relationship. We, in this system, actually, we combine a deterministic part that, as you see, limits enormously the amount of hallucination that the system does. But again, the combination, it's a very good step forward. But again, it's not necessarily a guaranteed solution. So unknown, no, it wasn't able. So it's again running on full frame. Let's it run for for a minute or so. So let's see if these converges. I can tell you that 80-90% of the time the answer is correct. And the other issue is that as you well know, small language models, large language model, visual language models, they never give the same answer. And so that was a challenge, because here mainly we are trying to constrain the system actually to be very precise in the kind of assessments that it does, and you see it doesn't speculate. So we remove the speculative part that is blocked. We check all the answers for consistency. But despite all this work, I strongly believe that the future is in models, in word models actually, that somehow learn about the physical relationship of the different elements, and so automatically reduce the kind of hallucination, the kind of situation that do not exist. Now it doesn't seem on the good path. I mean, we can still wait another minute just to see if the thing converges. This is what I call the demo effect, and is running live in front of me, and again, it is probably for just a very little threshold that is not able to nail that down, and so maybe we can stop here and see if there are questions. You have to trust me that it actually works. I have other examples, but I think you got the idea. Yes, I need to reset, otherwise this will keep running. Okay. So I'm gonna go back to these slides. Let's see, I'm gonna open them again.
While you open the slides, I want to ask you, what do you think word models can improve in all of this, maybe?
Pardon me, what?
How word models, the use of word models instead of
because simply, we had some rules that control what the system does. In a word model, you actually learn this kind of relationship and you reinforce them on a regular basis, and that mainly on one side requires much less parameters. So we are talking about tens of millions of parameters. These models, have 135 million parameters each, but a lot of stuff that is over there is not really useful. We are not using it. Word models can be much more precise, much more effective on this side. So. And I think, in 5 years from now, maybe I'm wrong, but this is what we're gonna see. Having said that, I don't know if there are questions on the chat. We are more than happy to present and to answer.
I think Anthony did a great job because he followed up with the comments.
With the questions.
With the comments and the questions. So that's fantastic.
Yeah, there's only one that I've not answered yet. It is, can I know the tops of the hardware, the max FPS of the video that this model can run on?
Pardon me. So with the FPS,
tops of the hardware and the FPS of the video.
The tops of the hardware. I said them before, Anthony. You should be more. You should listen. It's 1.35 tops. It's a Vivante NPU. The IP was put inside the chip, and actually works relatively well for YOLO. So works well actually for YOLO. And that was an interesting point. This project actually started from a question from Danilo that said, "But what about the MP2?" And we're really talking about YOLO implementation. And so I proved myself that this little board can do great stuff. no, if it's used carefully. And this mainly has been a challenge, to get all this running on this hardware.
Very good. And Andrea, Anthony, what are the next steps in this project? What are you
the next steps in this in this project is to add all the things that I was mentioning before. So the temporal memory, spatial memory, a component that is more deterministic and can make better use of the visual language model and the text language model. And another thing that would be really great, but it's tough, is to modify Llama CPP so that it can get a partial tile processed, because inside the scene we don't need to reprocess all the time, all the tiles, but only the tiles that are relevant to us, so that we could really run at way higher resolutions, avoiding to do what we did here now to reduce the resolution.
And then the fine tuning.
And the fine tuning, my gosh, I was forgetting.
It's my challenge.
Yeah, the fine tuning, it's it's definitely the next thing. And whoever is interested in this project, the GitHub is public. If you have improvements, ideas, and so on, we are really open to hear from you.
And last question before we conclude the workshop and all the session. Any call for action to the community tomorrow morning you would like to push?
Go buy the board, play with that, and do better.
The board is STM32
MP2, yes.
MP2 57.
Oh yeah. It's actually this board is the STM32 MP2 57F-DK.
Okay.
It is the cheap one, because there is also the AV one, but it's way more expensive. This is more than enough. And actually, the good thing, it has this connector that is Raspberry Pi compatible, so it's easy to add sensors, to add other components to this board, because we focused on video and images, but nothing prevent someone just to collect also, as Marcus was saying, collect other sensors, maybe ST sensors, and have a better sensing of the environment itself.
Excellent. Thank you so much, Andrea and Anthony, to be with us today, and for the wonderful workshop, and also for the brilliant idea about the narrative camera.
Thank you, Danilo. Thanks to you.
But the idea without
the execution.
The ideas alone are not enough, let me say.
Well,
and there was Steve Jobs saying that to turn idea in a solution, there is a tremendous amount of handmade work,
right.
Which is absolutely important, because then you find issues and you solve and you tune the idea until the solution works for real.
Yeah, I don't know if I told you, but I work for Next, so I met Steve.
So you know better this concept in practice.
Yeah, absolutely.
Very good, very good. There was. It's a brilliant project. Thanks so much to expose to AGI Foundation and to this workshop. Having said that, we are 3 hours and close to 10 minutes live, so it's time to say goodbye, and thanks to all, and especially to Andrea, to Anthony, as well to Marcos, and Lorenzo, and Ashutosh, and Rosina, and Peter. Thanks to all to make it happen. And
also to you, Danilo.
See you next time.
Thank you, Danilo. You're doing a great job, because
Thank
promoting these initiatives, it's fantastic. For me, it's always a pleasure to be here and show new things and new ideas.
Let's bring this prototype live